All right, morning everyone. How we doing? Just want to give you an update. 5 weeks ends Friday. Basically, you're not on your progress report. It's not going to be a numerical grade. It's going to be one of those basically scaled type things like a 1, 2, 3, 4 or whatever. Complete meeting, complete approaching, and complete missing. But they have just different terminology for that. So just so you know, for anybody who's missing stuff from the first 5 weeks or whatever, if you do it, I need to be emailed what it was because I can't go back and look at it. I'm not going to sit there and go back through everything and see if anybody's done it. If you email me by, let's say, Saturday night that you've done it and what you've done, then I can go back and incorporate it in. Otherwise, it's a lost opportunity. Today, we're going to review isomers at the end because it's going to piggyback into your isomers lab. We're going to talk about some functional groups today, just a couple of them, not many. Shouldn't be too long of a video. For next class, I do apologize about that one homework sheet, that page number 4. That's going to actually be your homework for tonight. So if you did it already, that's great. It's done for Friday. I don't know if I'm going to add another sheet or not. I'm still thinking about that. But you do have the lab. I'm going to put up a video actually made by Mr. Hilt, who went through and explained how to do the lab. He did it great, so there's no point in me reinventing the wheel on that. It's about 10 minutes, so you can watch that. He actually does page 1 of the lab with you so that you can see how to do it, and then there's page 2 and page 3. When you do, I'll talk about the lab at the end. All right, so here we go. Carbon needs to make 4 bonds. All right, it can make that in lots of different ways. It can have 4 single bonds. It can have 2 double bonds. It can have a triple bond and a single bond. It can have a double bond and 2 single bonds. All right, why does it need 4 bonds? Because it needs 4 more electrons to share with it. All right, it has 4 valence electrons. It needs 4 more. So if it has 4 plus 4, it gets to 8, which is that stable octet. It makes it more stable, makes it happy, makes it unwilling to do anything else after it. Okay, so that's why carbon needs 4 bonds. Okay, functional groups. Up until now, we've talked about hydrocarbons only, compounds that have hydrogen and carbon in them. Today, we're going to add in some other elements. All right. Outside of the halogens, we'll deal with them early. All the other ones generally introduce oxygen. And some of the ones next class will introduce nitrogen. All right, so it's where the oxygen is. This is very critical in your pattern recognition. This becomes a pattern recognition thing. You can't really glance over things. You really do have to understand or take note of where that things are. All right, these are molecules that result in features and changes to the molecule. All right, both chemically and physically. All right, in the real world, there's over 100 functional groups. The regions, or our level of chemistry, I guess we don't call it regions anymore, we'll focus on about 10. All right, so they'll have about 10. It's helpful to identify some organic compounds and get some general properties and characteristics of those compounds, so we're good to go with that. All right, so the first simplest group is hydrocarbons. That's actually technically a functional group. All right, these are compounds with just carbon and hydrogen and where they're associated. Now you have aliphatics are straight chains. All right, so you had alkanes, alkenes, and alkynes, which we talked about. We didn't really talk about aromatics, and we won't talk about aromatics. Aromatics are any of the ring structures that you take carbons and you form them into rings. Those become aromatics, and just like they sound, they do have smells associated with them. All right, they have aromas that they give off. All right, so that was really one of your functional groups, is just the hydrocarbons. Okay, now some basic things that you're going to understand as we go through these, that these are little groups of elements that are going to be helpful to recognize. All right, hydroxyl, we talked about this as being a hydroxide. When it forms an ion, it's a hydroxide. When it's attached to a carbon, it's a hydroxyl. All right, the reason why it's a hydroxyl versus a hydrogen ion or a hydroxide ion is because when it's bound to a carbon, it's going to be a covalent bond, and this isn't going to be released as an ion. So this can't not be released when it's in an organic compound. All right, so it's referred to as a hydroxyl group attached to usually the end, well, not necessarily the end. All right, this is used in organic acids. It's used in alcohols. That's probably about it. All right, carbonyl, all right, is a C double bonded O. and that can be in various places in there, but it's a C double bonded O. Just like up here, these don't form ions. These are actually bound, stuck together. So you're gonna see this carbonyl group, it's a C double bonded O. And sometimes you can get both of these together, all right, and it makes something different. And then there's what's called a carboxyl, which is a C double bonded O to an OH. Do I have it up on here? I don't. So what a carboxyl group is, a carboxyl group is a combination of both of these. So what I'm doing right here with my model kit, which unfortunately you guys don't have, but it works really well for people who like to see things. All right. So quickly, I'm just going to make a carboxyl group. Almost there. Sorry about the delay. I didn't think to make this one beforehand. And here we go. And one more thing. There we go. Okay, so to go back and talk about these sticks and sphere things, all right, here is a carbonyl group. Oops, here we go. It's a carbon sphere. So here's the carbon sphere. Here's the carbon has 4 bonds, 1, 2, 3, 4. Notice I don't have it attached to anything over here. That's something else that it could be depending on what the molecule is, but we're not really concerned with that part of the molecule right now. Here's a double bond. 1 bond, 2 bonds. So this shares 4 electrons or 2 pairs of electrons. All right. Here is a OH group, or also known as the hydroxyl group. All right. Here's the hydroxyl group. It's an O, or it's an O with an H off of it. And then the O has the ability to form a bond someplace else. All right, so that's where you get the OH, and a lot of times it's going to be attached to a carbon or some chain of carbons on here. Now to make a carboxyl group, these two things come together. All right, and there's your carboxyl group, the C double bonded O and an OH. All right, and then over here is a spot where it can bond to something else. For us, it's going to bond to a hydrocarbon, some version of a hydrocarbon, but there's other things it can do. All right, so there is the carboxyl group. All right, so this is kind of 3-dimensionally what it looks like. All right, and we see, okay? All right. Naming, common versus unique. So IUPAC is a technical term, all right, or a technical group of strategies to name compounds. A lot of these compounds were named way before the 1800s. All right, so this thing right here is called formic acid. It has 1 carbon. You don't know this yet, but this would be methanoic acid, methane, 1 carbon, and it's got the organic acid group, so it's methanoic acid, but its name is formic acid. All right, it sticks by its old name. We would name this as methanoic acid once we learn how to name these things. It's kind of like ammonia and nitrogen trihydride. All right, ammonia was named way before the nitrogen trihydride process came up. So ammonia is still 6. So formic acid, we tell you this because some people recognize the name. All right, acetone is another one. Acetone, technical scientific IUPAC name would be propanone. All right, because it's got a double bonded O in the middle of a carbon chain. We'll talk about that later, some other day. But this is acetone. All right, and you guys know acetone as nail polish remover. All right, acetylene. All right, people sometimes know what acetylene is because of acetylene, if you've heard of acetylene torches. All right, technical name of acetylene is ethyne. 2 carbons with a triple bond. All right, it's ethyne. All right, you should be able to name that one. All right, so these are the compounds that were discovered way before the IUPAC was formulated. All right, so they have 2 names. All right, for us, we're just going to deal with the scientific name. Okay, so here we go. This is going to be the kind of general format of how things are going to go. We're going to talk about the halide group first. All right, halide group, general formula is, it's a carbon bonded to a chlorine. Remember, halide sounds like halogen, so it's got a chlorine on it, or a bromine on it, or a fluorine on it, or an iodine on it. Now remember, when these things are branches, or when these things are part of another hydrocarbon, all right, they're named as branches, if you remember from last class. Chlorine would become a chloro branch. Bromine would become a bromo branch. Fluorine would become a fluoro branch. And iodine would become an iodo branch. All right, so what I'm going to do here is I've got the simplest hydrocarbon out there, which is this one right here. All right, can you see that we have a carbon with 4 bonds? Now the white spheres are hydrogens, and in this case, the green sphere is going to represent a chlorine, okay? So that's going to be a chlorine. So if this was all hydrogen, so I'm going to cover this one up. Let's assume where I'm grabbing is a hydrogen. What would this be called? Pause. All right, this would be called, if it was hydrogens, would be called methane. All right, one carbon, all single bonds, that'd be called methane. All right, now because we've got a chlorine on it, all right, we got a chlorine branch, so use prefix ending with O, so chlorine would become chloro, and then we still have our base root name, which in this case is methane, so this would be chloromethane. Okay, we don't need a number to tell where the branch is because there's only one possible spot. Okay, so that's kind of how you name these things. So right here we got a structural formula. I think that's a little bit easier to see. So you're going to draw that out. All right, you got 4 carbons. Now the key thing here is right here is your branch. You got a chlorine branch. All right, so you've got, so the 4 carbon single bonds would be called butane. And you've got chlorine in front of it, so it would be chlorobutane. Now, the only other information we need is the number to identify what carbon the chlorine is off of. So we can count from the right, and it'd be 1, 2, 3, or we can count from the left, and it'd be 1, 2. All right, we have to count from the left because it makes it a smaller number, so this would become 2. Oh, I didn't even appreciate the other branch on here, F, sorry, my bad. So we got 2 chloro. All right, and then down here we got a fluorine, and it's going to be up. We have to count from the same side. So this is 2-chloro, 3-fluorobutane. You could also call this 2-fluoro, 3-chloro if you went from the other side. The numbers stay exactly the same, so either one would work for the name on this one. All right, but this one actually stuck in 2 branches. Okay, so it's stuck in 2 branches, so you have to name both branches. All right, and you have to need the number of where it's located. Okay, good. Alcohols. Alcohols have an OH. If you remember what an OH was, we learned is one of those groups that you kind of need to recognize. All right, here's the OH in terms of the sticks and spheres. All right, and I'm holding where it can bond. All right, the OH is called, it's called the hydroxyl group. All right, alcohols change the base name to end in OL. So methane becomes methanol. Ethane becomes ethanol. Ethanol is the stuff that people drink or consume, beer, wine, spirits. All right, propane becomes propanol, butane becomes butanol, pentane becomes pentanol, hexane becomes hexanol, heptane becomes heptanol, octane becomes octanol, nonane becomes nonanol, decane becomes decanol. All right, and that's as far as we need to go. All right, so all you do is you put an OL off of it, and you do have to identify where that branch is, so you'll need a number in it from it if it's got multiple carbons in it. All right, for a 1 carbon and 2 carbon, you don't need a number because they're all the same numbers. All right, you get to 3 carbons, and you can have 1 propanol or 2 propanol, depending on if the OH is off the 1st carbon or the 2nd carbon. All right, so here we go. Here's our structural formula right here. So base name for this is butane. So what I'm going to do is I'm going to name this like it doesn't have any branches on it. I'm going to assume they're all H's. All right, so it's 1, 2, 3, 4. It's butane. It's got an OH branch. So what we do is we change the end to end, and you change the end to end in OL. All right, so it's butanol. And then the only other thing we'd have to do is identify the number of carbon that the OH is off of. Is it off of the 3 carbon if I go from the left, 1, 2, 3, or off the 2nd carbon if I go from the right? We got to take it off the right, so it's 2-butanol. Okay? Ethylene glycol. All right, I have a pretty good story for this, but we're not going to go into it. Ethane diol. So it's ethane with 2 OHs on it, so it looks like this. All right, this is the stuff found in antifreeze. Antifreeze is actually an alcohol. I wouldn't drink it. It kills people. All right, there's somebody in Liverpool who killed 2 husbands with it. I think I brought it up earlier in the year. You can look it up. Just look up, I forget what her name is, but just look up Liverpool, New York, husbands killed by antifreeze. All right, and there's a story. There was actually, I don't know if it was True Crimes or one of those investigative stories or 2020 or something, actually did a story on her. But she was successful in killing 2 husbands by giving them drinks with antifreeze in it. So don't drink this alcohol. Don't drink diols. They're not good for you, even though they do smell sweet. That's why if it's leaking from a car, it's deadly for your cats or anything that lives outside because it can kill them. Okay. Organic acids. So we did halides. Now we're doing organic acids. General formula: C double bonded O, OH. All right, so it's that structure. It's combining that carbonyl group and the hydroxyl group that we talked about in the beginning. All right, it's this thing right here, and then where I'm holding it, it's going to be attached to something. So you got to look for that double bonded O and that OH. All right, how do you name these? Is you end them in oic acid. So you got methanoic acid, propanoic acid, butanoic acid, pentanoic acid, whatever. Okay, so here we go. The condensed formula. So I'm sticking in condensed formulas because sometimes it's easier to see it this way. All right, this is the Ku group. For people who've taken living environment, I know you guys talked about Ku groups in biochemistry. All right, so condensed formula writes it like this. If we draw out the structure makes it a little bit easier. All right, it's whichever one you prefer. All right, but notice we don't just combine all the carbons, hydrogens, and oxygens, because then that would be C4H8O2. It doesn't really tell you what it is. It's confusing to do it that way, so we do a condensed structural formula or condensed formula. All right, so here we go. You got 4 carbons, 1, 2, 3, 4. If these were all H's, it'd be butane. All right, but it's got a double bonded O and an OH. This is always going to be on the first carbon or the last carbon or the first carbon. It's never going to be in the middle. So it's easy. You just look at the end of the carbons. All right, so this is butane, drop the E, add oic acid. So it's butanoic acid. You don't need any numbers for organic acids because it's always on a terminal carbon, which is essentially going to be the first carbon because you always count from that side. All right, so that works out well. So that's butanoic acid. All right, so those are the functional groups that we're starting today. All right, next class we'll do other ones. All right, so I just want to review isomers again. All right, in here, so I think it's easier with this. So here I have the carbons with all the bonds that they need on them. All right, so if I drop this down and look at this like this, I think it's a little bit easier to see. All right, so you've got these carbons. You got 4 carbons. In this case, it's in a row or in a line. All right, these things would all represent hydrogens. I didn't put the hydrogens on to confuse the color, but it does help us see some things. So I'm just going to try to do this so I can pin this down with my, there we go. I think this will be a little bit better than looking at the computer screen. All right, so here we go. So we got 4 carbons. This would be called butane. All right, if we want to make an isomer of it, could we take this carbon here off? We're going to take this carbon off. All right, and then put it down on this side. All right, so I'm going to attach it. What do we have here? It looks different because I kind of put it in a different shape, but it's still, if I take my finger, I run it across, and I get carbons, 4 carbons in a row. This is butane. Remember, I'm going to go back to the computer screen. Remember, isomers are the same number of atoms, but arranged differently. Are these arranged differently? No. But what if I take one of these and put it on, not the same carbon, move it over a carbon. So I'm going to move it over a carbon. Now we have a different molecule. Now I can't get all 4 in a row. I can only get 3. All right. It used to be butane. Now it's called propane. Got 3. And then I got this branch off of it. It's a 1 carbon branch. So this is methyl propane. And we need a number to say what carbon it comes off of. This is 2-methylpropane. All right, so that, remember, that's just a quick review of isomers. Mr. Hilt will talk about that in the lab as well. All right, I just want to show you, you can do isomers with different elements. I'm not going to get into that with this lab right now. All right, but you can also do isomers with the location of the double bond. If I look at this molecule right here, depending on how I arrange it, all right, I might be able to make something that stands up like this. All right, you can see that that stands up. Those are all just empty things up there. So this is 5 carbons with a double bond here. So you've got 1, 2, 3, 4, 5 carbons, so it's pent. It's got a double bond ene, so it's pentene. Now what pentene is it? If I count from the bottom down here, 1, 2, 3 pentene, or I count from the top, 1, 2 pentene, I have to pick 2 pentene because 2 pentene is a smaller number. Now, a simple isomer is just change the location. Can I change the location of the double bond? If I do this, I'm just moving a carbon from one end to another. Now I get 2 pentene or 3 pentene. So that's the same molecule, right, as I had before. Because I remember these things are 3-dimensional, they can move whatever way. Now what if I take this carbon here and put it off of that carbon? Now what do I got? Oh boy. Now we definitely have something different. We cannot get 5 carbons in a row. We can only get 4. Now, when you're dealing with double bonds, the double bond has to be in the main chain. So I can get 1, 2, 3 carbons this way, or 1, 2, 3, 4. So I have to take 4 because that's our longest chain of carbons. All right, so 4 carbons is bute. It's got a double bond, so it's ene, so it's butene. Now, is it going to be 1 butene, or is it going to be 1, 2, 3 butene? It's got to be 1 butene, so this is 1 carbon. So this is 1 butene. And then we have this branch up here off of it. That branch is a 1 carbon branch. It's methyl butene. So now we need the numbers. So we have 1 butene, so it's technically methyl 1 butene. We need to know the number that the methyl group's off of, so it's 1, 2. So it's 2 methyl, 1 butene. Okay? Just showing you how, remember, isomers have different properties and such. All right? So those are in that way. Okay? And so isomers lab. So by Monday morning, if you want, I can check your data to make sure you have all the right molecules and drawn out. When you draw them out, you have to draw them out with carbons and hydrogens. Try to do each one on a page. Like you're going to have to do isomers of butane, isomers of, is it hexane or pentane? I can't remember. And then isomers of butene. All right, so do one set on one page, one set on another page, one set on another. So you have 3 pages. All right, please use the scan function either on your phone. It makes it way easier for me to look through all the pages together, all right, versus as 3 separate pictures. All right, so that's review by Monday morning. I will look at them Monday and get them back to you by Monday night. And then the final write-up is due Wednesday night. Okay, all right, have a great night. Talk to you later.